One announcement is the napkin ring problem, which was a homework problem, which was like the demonstration I did here in class with this big weight, which I took away. The solution that we gave you has an algebra mistake and doesn't give that beautiful answer that the final motion is 0 velocity and 0 angular velocity. So it's just an algebra mistake. That's the problem, is it?
They don't go to the point where they show that the two cancel each other out. I think that
they never finish the problem in the solution. They, being I don't know who, they I guess is us, but I don't know who us is in this case. But so the solution isn't complete. So is it an error or just it's not finished? Somehow they didn't get to that beautiful answer, somehow or other. So error, question mark. Okay, so today we're going to talk about relative motion. This is this confusing kinematics, confusing geometry. I'll try to make it less confusing, but it's a tricky topic. Any logistics questions about the course, the exam, things like that? Where's the exam? I think it's in the same spot. Is it not? 155. Is Luke here today? Okay, Luke said he did a poll about what people would like different in this class. So one thing he said, people would like to know why are we doing what are we doing? A little bit more. So let me just do a little bit on why we're doing what. Overall, we're doing this thing called dynamics because this is mostly mechanical engineering curriculum. Mechanical engineering machines move, and you'd like to know how they move. How they move is governed by Newton's laws and Euler's laws. The angular momentum one is called Euler's laws. And you'd like to know how things move and be able to predict things about how they move. What is their motion? Or given their motion, what are the forces? So you can figure out whether the parts will break or they're strong enough and so on. That's the overall thing. Within that, how do we pick topics? This course more or less has a historical definition. Very similar courses have been taught for at least 50 years and probably more like 100 or 150 years. Why exactly this balance of topics? It could be argued the balance is shifting with time, but not shifting very fast. I would say industry is shifting faster than the curriculum is. So our curriculum isn't fine-tuned for industrial needs, but more or less it gives you good background. I have found, however, as I told you at the beginning of this class, that if you take the formulas you learn in this class, the exact calculation skills you learn in this class, that almost nobody uses them in industry. Okay, that's a depressing thing about this class. So you say, why are we learning exactly these formulas and so on when nobody uses them? I don't really know. Okay, that's sad. Sad fact.
Design the curriculum?
What?
Don't you design the curriculum?
I am amongst those who design the curriculum, but there's all these competing forces from various directions which make it very hard to change the curriculum. And like one of those competing forces is just what are all the courses taught in America? So almost the same course is taught across America. All the textbooks teach the same things. People expect the same things in the curriculum and so on. So I can fight it, and I do fight it. This course is a little different than most other courses, but can't change it totally. Okay, next. What's it really good for, this course? One is building your physical intuition about how things work. So if all you're doing is algebra, you're not getting out of this class what you should. 2 is algebra skills, just general calculation skills. 3, general problem solving skills. 4, unlike dynamics, statics and strength of materials is used by millions of engineers every day. So the formulas, the basic formulas you learn in statics, sum of forces equals 0, sum of moments equals 0, stress equals pressure divided by area, bending moments given by EI over rho, bending moments given by EI over rho, right? There you go, very good. Those things are used every day by engineers. Some of that overlaps hugely with this course, so building the skills in this course build static skills. Okay, next thing, Matlab. Why so much Matlab in this class? So this is something which is different from the main curriculum in America, and why do I push it? Is because Nowadays, how do people calculate things with computers? What do they use? Not Google, not Facebook, not Twitter. They use computer programs like, for example, Matlab. Why Matlab instead of Maple, Mathematica, MathCAD? Any others that people like? What's the one that's used in the lab for the, what? Scilab, Python, C++, Java, is because for engineering purposes, Matlab is more or less coming to be a national standard. Even though it's a company and a product, just like Microsoft is a company and a product, it's become a national standard. Matlab has become that. Separate from that, Matlab is a Cornell standard, whether or not it's a national standard. So the language you use is the one that's used at Cornell. So why Matlab? It lets you solve problems that you can't solve with pencil and paper in this class. By solving them, hopefully you build up intuition. Drop that whole thing. You hate dynamics, you're never going to use dynamics, you hate statics, you don't want to know algebra, you hate the whole subject. If all you do is learn MATLAB, you're learning something that's going to be useful for you for your later courses at Cornell and perhaps for your engineering career. So of those who whine about MATLAB in this class, a vast majority are grateful for it when they take later courses. So separate from the fact that it's an appropriate thing to do in this class, it's also an appropriate thing to do just for you to learn how things work. Okay, that's the overall motivation. Now, let's go to today. Motivation for what we're doing today. We're building up complexity of problems. Now, we've been mostly dealing with single parts, machines that are made of one part, like a bullet, or a object moving through space, or a pendulum swinging. And now, when you notice that when you look at real machines, they have interacting parts. Some kinds of interacting parts are easy to deal with, like gears on shafts. You've already dealt with that. Why? Because each one has a simple motion, and all you have to do is couple them in a simple way by matching velocities. Some machines have more complicated motions because the parts are connected to each other, not just connected each one to a hinge in the background. So you'd like to be able to begin to understand more complicated machines, and one way to think about these machines is having some kind of relative motion. So to start with, we do this kind of abstract thing, and I'm going to start with what I did last class and then do examples using that. So it's going to start out abstract, but at some point it will look like some kind of machines and mechanisms. Okay, when we do the laws of mechanics, we have to use some reference frame or coordinate system that makes sense. Usually in mechanical engineering, we are happy thinking of things glued to the room as being a so-called inertial reference system, fixed reference system, Newtonian reference system. It's when we measure coordinates using that reference system, it tells us the laws of mechanics are accurate. So now we're looking at something which is moving around. So some object. You can draw whatever crazy object you want. You don't need to match this shape. And we call this object B for body, and this thing is moving around. As it moves around, there's some reference point on it, which we can call O prime. And we're interested in the position of this. That's position of O prime with respect to O, or sometimes we just write the position of O prime, where the O is implicit. Now actually, we're interested in watching something which is flying around over here, some P, and this is some point which is not attached to this body, but which is moving around on the body. Now we're going to be thinking about machine parts and pieces of metal and stuff like that, but just conceptually you can think of that as a bug which is crawling around on that part. And it has some motion on this part. So for example, on this part we could draw some coordinate system x prime and y prime that has unit vectors I prime and j prime. And we could look at this vector, the position of P with respect to O prime, and we could write that in terms of x prime and y prime coordinates, just like we could write it in terms of x and y coordinates. And we can keep track of this angle here, theta, and we can talk about this omega vector, which is theta dot k. So the overall problem is, let's say we are given the position of O prime with respect to O as a function of t, and we're given the position of P with respect to O prime, Let's say we're also given the velocity of p with respect to the body, and we're also given the acceleration of p with respect to the body. From this, what we would like to calculate is the velocity and acceleration of p with respect to O. So we want to know, because we're dying of curiosity about everything, the position of p with respect to O, the velocity of p with respect to the fixed frame, and the acceleration of p with respect to the fixed frame. So first off, we have to remember what these funny things are here, these things which are velocity and acceleration relative to a moving frame. Until this point in the course, when we said relative to, it meant subtract. Hey Luke, would you come in time for my speech that I gave on your behalf?
Yeah.
Was I close enough?
Excellent.
Okay. Did they think it was excellent? They can tell you. Okay. Until this point in this class, when we said relative position, relative velocity, relative acceleration, it meant subtract. You could use the analogy, how much money do you have relative to me is how much money you have minus how much money I have. What's your position relative to me is your position minus my position. What's your velocity relative to me is your velocity minus my velocity. What's your acceleration is your acceleration minus my acceleration. That was true when we had relative to a point. Now we're doing relative to a reference frame, and it has a different meaning. It's a related meaning, but it's a different meaning. It's a generalization of that idea, and no longer can we use subtract. What we mean by relative to this object is you get on board this object. Think of it as a space station. The windows are blocked off, so you can't see outside the space station. You watch something move around, and relative to the space station, that means using a coordinate system glued to the space station, you calculate the velocity and the acceleration. So one way, if you want to be very literal about this, is you can say this velocity is p with respect to f. If you want a calculation rule for it, is x prime dot I prime plus y prime dot prime times j prime. And this acceleration of p with respect to f is x double dot prime I prime plus y double dot prime j prime. Now, in fact, we might never use this formula for the definition. It just gives you a concrete way to think about what the definition is. For example, we might calculate this velocity and acceleration using a polar coordinate system which is glued to this object. Or we might calculate it using a different Cartesian system glued to this object. All of those different ways give the same answer, just like back here when we calculate velocity and acceleration using Cartesian coordinates or Cartesian base vectors or polar coordinates or polar base vectors. The velocity vector or acceleration vector is the same both ways. It just looks different. It's represented with different base vectors. Here, we can use different base vectors and represent it different ways. And this is just one of those ways of doing it. Okay, now this all looks abstract, and it's going to even look more abstract when I write these basic formulas, which are the key formulas. What's the position with respect to O of this P is equal to the position of O prime with respect to O plus the position of P with respect to O prime. That part is just straight out of what we did before we got to here. Now we get to these funny formulas for the velocity. We'd like to know the velocity of P, and we say the velocity of P with respect to the fixed frame, which we can think of as just the absolute velocity of P. So if you want to be really careful about it, what you mean by the absolute velocity of P is relative to some reference frame, the fixed reference frame. And I'm not going to do the derivation here. The derivation's in the book. And I think you're better off getting used to the formulas before you do the theory of deriving the formulas. So get used to it, then go back and do the theory, and then get used to it again. What is the velocity? It's the velocity of O prime with respect to O, which we could just call the velocity of O prime, plus, and now we have two terms in this velocity, and what the two terms are two intuitive things. One is you pretend that this thing is not rotating, and just look at the velocity of this point relative to this point, and use our same old relative velocity formulas, and this gives the velocity of p with respect to b, which is the same as the velocity of p with respect to O prime, if that object b is not rotating. On the other hand, if the object is rotating, but the bug is dead, then we get a relative velocity, which is omega cross the position of p with respect to O prime. So what's the velocity of this point? It's the velocity of this point, plus how fast the bug appears to be moving here, the velocity of it, plus the motion of a point fixed to the rigid object directly underneath the bug. So the velocity of a point directly underneath the bug relative to this is just that omega cross r term, and then we look at the velocity of the bug relative to that, which is the velocity of the bug in this moving reference frame. Okay, so this one's intuitive. The acceleration formula is almost intuitive, but not quite. The part that's not intuitive, we're going to try to make a little bit of sense of, but it's not as straightforward as the velocity formula. So let's just stick with the things that seem intuitive. Yes?
Oh, never mind.
Yes?
Is there a difference or incorrectness about writing velocity p with respect to O instead of p with respect to, like, the reference frame?
So we put the velocity p with respect to O. That would be okay, because when in doubt, when you don't mention a reference frame, you're assuming the fixed reference frame. So it depends on who you are. Different people are more fussy about this one way or another. I'm not so fussy about it. So if you just write velocity of a point, you mean relative to some fixed point and as measured in a non-rotating reference frame that has an origin at that fixed point. Now, why get fussy? I didn't. Okay, just put this in parentheses in your mind, so it doesn't distract you from the flow of the argument. But why get fussy is because all of these formulas don't just apply for calculating the relative velocity and acceleration of this point relative to this reference frame, but they also apply if we have another object moving relative to this one, and we want to calculate the velocity and acceleration relative to this reference frame. So if we have another object that we can look at relative to this one, we can use this formula recursively, once to figure out what the velocities and accelerations are on this frame given this information, and then once to go from here back to here. And we can do it recursively again and again if we have a sequence of parts. If you intend to get to that recursive definition, then you need to be very careful about what reference frame you're using every time you write the velocity and acceleration. Now, we are not going to get that far in this class, and there's no point in getting there until you're comfortable with this. But if you want to get there, then you have to be very fussy about the notation. Okay, parentheses is over. What's the acceleration of this point? It's the acceleration of O prime with respect to O. That's easy. Then we can think of a dead bug here, or a particle marked on the object underneath the bug, and look at its acceleration, and that has two parts to it. It has a minus omega squared, the position of the bug relative to O prime. And in general, this term, in three-dimensional version of this formula, this is omega cross the position of p with respect to O prime. But we're not going to do this three-dimensional version, but just so you know. And by the way, when we write omega, we mean omega of this body relative to the fixed frame. And if we're going to be doing that recursive stuff, we have to be very careful about what the definition of omega is. Omega of what object or reference frame relative to what other object or reference frame. What else do we have? If we're looking at the dead bug, or the piece of pencil mark underneath the bug as it's crawling, there's an acceleration due to the fact that that particle is going in circles relative to O prime. And even if this thing is dead, and even if O prime is not moving, this can have an acceleration in this direction due to the fact that this might be rotating faster and faster. So what do we have so far is this accelerates because this whole body accelerates. This accelerates because there's a centripetal acceleration. And this accelerates because there's a tangential or circumferential acceleration due to the angular acceleration of this object. Now what else do we have? Is even if the object is not moving, even if it's not rotating, even if it has no rotational acceleration, the bug itself could be accelerating, and that gives us this acceleration of p relative to this moving reference frame. Go ahead, ask your question.
For acceleration with O prime with respect to and velocity, we're assuming that's not a rotational acceleration of velocity?
What are you looking? Just
with respect to O.
This is not rotational.
Yeah.
Right. This is just a position of a point relative to another point.
Okay.
So you're just looking at 2 points, and there's no rotation in that first term. So whether or not this is rotating doesn't affect this term. You're just keeping your eye on these 2 points. The rotation shows up in this term and the last term, which is the hardest one to understand, which is 2 omega cross the velocity of p with respect to the moving frame. And this is the Coriolis term, and I will try to give you a little bit of intuition about this term. Leaving this term off, everything is intuitive. You got a furrowed brow there? What? This says omega cross V.
Oh, dot.
There's no dot products anywhere on the blackboards.
I saw omega cross V, but the other ones are omega dot.
Right. Well, this one is an omega cross R.
But there's 2 omegas.
There's 2 omegas, right. One thing you can do is a dimension check, a units check. Acceleration is meters per second squared, distance per time squared. Here's acceleration. Omega is angle per unit time, which is 1 over time. 1 over time squared times distance, that matches. Omega is 1 over time. Derivative is 1 over time squared times distance, that matches. Acceleration, units match. And here we have omega 1 over time times velocity is distance per unit time, so we get distance over time squared. So was yours the unit question? Was that the motivation of your question? Okay, does that answer it? Okay, so let me do a more concrete example. It's still abstract in a sense. It doesn't look like a machine, but it makes it so we can think about these things. So what we're going to have is a truck with a turntable with a bug. Okay, so we're going to draw a truck here. Here's our truck. And on this truck, we're going to put a turntable, which is rotating like this. And on this turntable, we're going to mark a line. So we have a line marked on the turntable. And on that line is a bug, which is in a hurry, scurrying across the turntable, following the line. So here's this little bug, which is following this line. And we're going to keep track of this turntable by looking at this distance x. We can call this thing O. We can call this point here O prime. We can call this bug P. As this bug moves along, we can keep track of how far it's moved along by how far it is from the center of the turntable, and we'll call that distance R. And we can look at how far the turntable is rotated, and we can call that angle theta. And the question is, given x dot, x double dot, let's put a I here and a j here. Let's say we're also given r dot, and r double dot. Let's say we're also given theta, theta dot, and theta double dot. And to keep it simple, let's say that theta is equal to pi over 2. And these other ones we can leave general. And we want to know what is the velocity of bug, which we would call Vp, or what we mean by that is Vp relative to the fixed frame. And what is the acceleration of the bug? And we can call this the acceleration of P, or the acceleration of P relative to the fixed frame. Okay, so what we'd like to do, basically, is plug in these formulas. Really, we should answer the first question, which is the position of the bug. And usually for problems like this, you're not going to get very far unless you solve this problem, this geometry problem first. So this one actually goes first. It's a little less interesting, but it's a little tricky thing you have to do. Okay, I want you to do that calculation right now yourselves, and that's the quiz. That is, I want you to answer this question in terms of these variables with this one number given, everything else variable, find out the answer to these questions, all three of them. And I'm going to make that the quiz question, and then you'll self-grade it whether you get it right or not. And as you do it, if you want to ask me questions, you can. As you do it, I'll be setting up my computer to record your quiz score. Yes?
The line that goes through the bug's path, that goes through your O not time also, or like further extended?
No, does not.
Okay.
Wait, so O not is the truck's starting point?
Say again?
The O not is the truck's starting point?
Doesn't have to be. It's just a reference point for measuring the position of the truck.
The starting point of the truck?
It has nothing to do with it because we're given not x as a function of time, but at the time of interest we're given x, x dot, and x double dot. So it doesn't matter where the truck started or when it started. Does that answer your question? I almost clicked on the exam if you would have been. Oh, I didn't broadcast it yet, so you're safe. Okay, to start with, could everybody vote anything?
Is there a theta of importance with respect to O-non and
You're interrupting something very profound here. What was your question?
Is there a theta of importance between O-non and O-prime?
No.
No?
All that's important about O prime and O is the X. This line
Okay.
doesn't matter where it goes. And now I got to start the song over again.
And he looked like he might have been a hat check clerk
Wait a sec, I got to start at the beginning.
at an ice rink,
Got it?
which in fact, he turned out to be. And I said, oh boy. Oh yeah. It could be you. Is the sky blue sky? Satellites.
Okay, did you get the key words there? Did anybody not catch the key words?
There's something about a hat check clerk.
She said, and it's the title of the song, let X equal X. Key equation. You want to hear it again? You can look it up. For $1, you can have it on your own computer. It's Laurie Anderson. It's called the title of the song is Let X Equal X.
So, the title of the song is a hat check.
She said something about a hat check boy or something. I don't know what that has to do with X equaling X, but okay, while you're working on this problem, one of the things one can do in the web besides Facebook is ego surfing. Ego surfing, you guys can't do much of it yet, but later in your lives you'll be able to do it. So you look up some show called Science Friday, and you click on video for Science Friday. And you say, why do you take this class? Because why take a class like this? Well, you go to Science Friday and you see a class. You take a class like this because dynamics, okay, it might not be useful, but dynamics is fun. Okay, so here's a video on Science Friday. I'm not going to show you the whole video, but see if you can recognize anything in this video.
Bicycles are beautiful, like the stars are beautiful. And one likes to stare at the stars and wonder how they work. You like to stare at bicycles and wonder how they work.
This week's featured video on Science
Is
Friday.
that your only bit?
Is that what?
Is that your only bit?
My only bit? And no, it's all about me. Like everything in this world. So, okay.
Bicycle.
Okay. I could listen to that all day. Okay, write down your answers such as they are.
No, I'm not done.
Who's not done? Who is done? Okay. 2 minutes more.
That's nice.
Okay. 30 seconds more. Yes?
That R given, is that R P with respect to O prime?
It is the distance from O prime to the bug. It's not a vector. It's a distance. Okay, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. 5. Term acceleration formula is the subject of this quiz. It's called the 5-term acceleration formula. I've lost my clicker thingy. Help? Okay. Okay, so how are we going to work this out? Well, we've got to decide how we're going to plug in this formula. For this case, let's call this object here the fixed frame. We'll use some origin here or here, and we'll call, the moving body, and we'll call this the fixed frame is this thing attached to here. And in order to plug in this big formula, we have to plug in the terms. So for example, what is the position of O prime with respect to O? That would be just xi. So we can plug that in. What is the position of P with respect to O prime? Well, if we put here a coordinate system I prime and J prime, and you could just as well use a polar coordinate system. You can use polar coordinates or a rotating Cartesian coordinate system. This thing is equal to R I prime. And at the moment of interest, so this is at theta is equal to pi over 2, I prime is equal to J prime, so this is equal to R J. I say I prime is equal to J, this is R J. So even though we're looking at the position relative to this moving body, we can express that position vector back in the fixed coordinate system, the one that the x and y, ij non-rotating coordinate system. Now what else do we have to worry about? We have to worry about what is this thing omega. Omega is theta dot k. What is omega dot? That's equal to theta double dot k. Now we have some harder ones. What's the velocity of P with respect to this moving frame? It's equal to R dot I prime. And at the moment of interest, I prime is coincident with J. So this turns into R dot times J. And this is at theta is equal to pi over 2. Now what else do we have to worry about? We have to worry about the acceleration of P with respect to this moving frame. And that's R double dot times I prime, which is equal to R double dot times J at theta is equal to pi over 2. Now, if we want to figure out the position, velocity, and acceleration, all we do is plug in these things. So let me plug them in, and then I'll take questions. So what is the position of P with respect to O? It's equal to xi plus rj at this instant in time. What is the velocity of P with respect to O? The formula we're going to plug in is it's going to be the velocity of O prime with respect to O plus the omega cross the position of P with respect to O prime plus the velocity of P with respect to the moving frame. Now we know all of these things. This is x dot times I. I didn't fill this in, but this velocity is just straightforward differentiation of that position. Here we have theta dot k crossed with rj, and that's something we can calculate easily. And here we have r dot times j. So if we add up these three terms, k crossed with j is minus I. So we get the velocity of P is equal to x dot minus theta dot r in the I direction plus r dot in the j direction. Now what about the acceleration of P? Now we're going to plug in the 5-term acceleration formula so somebody can see what we're doing. Let's write the formula down, and then we'll plug in terms. Acceleration of O prime with respect to O, plus, and let me just do it in the same order as up there, minus omega squared, the position of P with respect to O prime, plus omega dot cross the position of p with respect to O prime, plus the acceleration of p with respect to the moving frame, plus 2 omega cross the velocity of p with respect to the moving frame. Okay, now we just plug in all those terms from all these terms. What's the acceleration of O prime with respect to O? X double dot times I. Let X double dot equal X double dot. Okay. Then we have minus omega squared times its position, which is minus theta dot squared times Rj. Then we have plus omega dot, which is theta double dot k, crossed with this position, which is Rj. And then we have plus this acceleration, which is R double dot times I prime. But at this instant, I prime is equal to j. So here's an R double dot here. And then we have plus 2 theta dot k crossed with R dot times j. Then if we want to turn this all into x and y stuff, we can try to collect terms. What do we have in the I direction? We have an x double dot. K crossed with j is in the minus I direction. So we have minus theta double dot r. This is not in the I direction, but this is in the I direction. K crossed with j is again minus I. So we have a 2 theta dot r dot minus 2 r dot theta dot. And this is all in the I direction. And then in the j direction, we have minus theta dot squared r. And we have a plus r double dot. And this is in the j direction. So copy that down and then ask me questions about anything. The usual suspects here.
So my question is for the position. Why isn't there a y component? Like I understand that, like since the truck is only moving in the x direction, that the velocity should only be x naught. But I don't get why there isn't like a y. Like it should be xi plus yi plus r.
Yes?
I would just like to see the derivation where we get Rp with respect to O prime is equal to R of J.
Okay. So the question is, how did I get this?
I get where the I came from, but
Okay, it's I prime and it's j.
I don't see.
Okay, so here's I prime and here's j prime. And in this moving reference system, the position of the bug is r times I prime. No question about that, right?
Yeah.
At the instant of interest, we were told that theta is equal to pi over 2. When theta is equal to pi over 2, this is a right angle, and I prime is coincident with j.
Okay.
So at the instant of interest, the position of p with respect to O prime is r times j.
Oh, okay.
It's not true for all time. We can't differentiate that expression, but the whole trick is that the differentiation, these formulas have the differentiation built into them. So you look at the instantaneous configuration, and this gives you the velocity and acceleration in terms of the instantaneous configuration. Does that address your question?
Yes.
Yes?
So what I did is I just started with the position vector and I just kept taking derivatives.
If you just start with the position vector and take derivatives, that is correct. You can do every problem that way, and you don't need to learn this material at all. It's just the longer way to calculate.
Yeah.
Any other questions? Yes?
You have velocity in the last term of the acceleration. Velocity with respect to the moving reference frame. That's just along the radius, correct?
That's correct, because you get on board here, you ignore the truck, and you look at, on this reference frame, what's this velocity, and that's what you see. Okay. I have negative 1 minute. I can accommodate that. I will talk backwards for 1 minute.